All right, everyone. I am excited to welcome up Justin Norman, Vice President of Data Science and Analytics at Yelp, to walk us through his presentation, Machine Learning Product Experiments at Scale. Take it away, Justin.
Thanks, Sam. It's a pleasure to be here, and I appreciate the invite. Looking forward to sharing with everybody. So we're going to get right into it. We've got quite a bit to talk about, and I hope this will be useful. So as the program in the slide says, I'm Justin, and I have the privilege of leading Yelp's data science and analytics teams. So that's an overly vague title for a pretty broad set of functions. But the reason I'm here today is because as a part of my role, I also lead the data product management team at Yelp. So this team is primarily focused on building powerful data platforms that enable analytics, data science, machine learning, and automation. So today we're going to spend some time talking about a particularly challenging but equally important area of investment for our AML product management team, which is building machine learning tools for experiments. So you might ask, why even have this conversation at all? So machine learning systems have, over the course of the past decade or so, advanced to the point where we're not just building models for science and fun, research, etc. And first of all, that's a really good thing. But it also means that we actually need these models to work. And they have to work as designed for the use cases that they were designed for. And they have to work relatively consistently and then be deployed at scale to millions of users that are having billions of different interactions. So if you're thinking this sounds familiar, this is the promise behind all the machine learning and AI hype that we've been talking about for years. And so now we're getting into the practicality of how it's applied in the real world. But as it turns out, this is a pretty hard problem. It's pretty hard to do, especially the first time. And unlike deterministic software, patching a bug or a bad UI behavior isn't straightforward at all. Different users are intended to get different outcomes depending on the features that are encoded into a particular model. And then those models are ultimately delivered via a complex production pipeline, like we mentioned at the top of the presentation. So as you can see on the slide here, even the biggest tech companies in the world often don't get it right. And the social and business consequences of them not getting it right are astronomical. So if we think about some of those cases from the previous screen, we have to ask ourselves what went wrong. Well, a lot of things went wrong, clearly, but let's try to enumerate a few things that are useful within the context of experimentation. The first thing is that these companies were either accidentally running experiments when they should have been running a rollout, or in other words, deploying a large-scale test, or they weren't sure which one of those things they were doing. So to do better, we first need to differentiate between testing and experimentation. Moving forward, when most people say the word experimentation in machine learning platform, they typically mean literally running dozens to thousands of iterations of parameter optimizations over known and unknown data sets, trying to facilitate some kind of model training. And when something goes wrong, like in the previous slide, we need a way to quickly roll back and look for the problem. So clearly we need some kind of revision control and state management and some tooling to be able to keep track of all of those things. And as we go forward into scaling, typical model evaluation techniques are actually inherently small scale and small data. But as we all know, that's not how the real world works. And so our systems need to be able to look at the data and the performance of the model in near real time, both in the online and inference use cases. And then once we are able to inspect that, we need to be able to capture the real world user experience with our downstream systems, machine learning systems, which frankly is going to mean probably a lot of Kafka and Kubernetes, and we'll kind of talk about that. And finally, is there a way for us to push the boundaries of dynamic traffic allocation? So obviously, not every user experience should be the same. That makes sense. But is there a way we can build a model that performs better or best in a limited set of constraints, and then prioritize others for different constraints? How do we even know which model is best without running a bunch of tests for years to be able to know what to present? So there's actually a set of techniques in the multi-arm bandit family that can be pretty useful here, and we're going to get to that towards the end. So let's start with the pre-production environment. This is probably the most typical ML development cycle that we're all familiar with at this point. So I'm going to zoom out a bit and then talk about the key capabilities, and then talk about how Yelp approaches it today in the real world. So there are quite a few proprietary tools available on the market which help you maintain version and history of any particular model and model run. There's far too many to list here, and many more which claim some capability in this space. But a thing to keep in mind is that introduction of these types of tools into your environment are going to bring challenges as well. There are many options of varying maturity, and they don't all play with each other in the ecosystem. For blank canvas companies, those that haven't invested a lot in data or machine learning infrastructure, or for startups, these can be excellent time savers towards giving extremely powerful ML capabilities to your developers without a lot of time spent in the platform. However, for companies like Yelp, who have invested a bit more over time, this is a bit more complex for us to take on board, given our existing scale and our pipeline diversity. So for us, it becomes more of a cost-benefit analysis to determine whether or not we build or maintain in-house versus we buy something or integrate an open source capability. And we'll definitely talk about some real cases where that happened for us. But at a very high level, the things we need to be able to do are really capture the key points of the machine learning development cycle. So, we need to be able to create a snapshot of the model and maintain that, dependencies, configurations, as well as keep track of the artifacts, the versions of data, and any associated images that we might generate or plots. We also need to be able to build each one of our runs in some kind of isolated environment. This is probably going to be a containerized environment nowadays, but still, need to be able to isolate it. And then also the performance metrics of the model itself. So, it depends on the technique, of course, that you're using, but some common performance indicators are in the family of things like ROC, AOC, or loss functions. And finally, we want to be able to inspect or compare all these different attributes for one model to another to determine which one is actually the right one to put into production. So for Yelp, we recognize that any in-house solution we built would probably be quickly surpassed by the ever-increasing capabilities of all these open source projects, and that buying something was more than likely not going to scale well to the complexity of our existing environment. So we kind of split the middle. So we invested in a bunch of open source libraries that aligned the best with our needs, and then constructed some thin wrappers around them to try to allow for easier integrations with some of our legacy code. In the cases where open source tools lack the capabilities that we need, we're contributing solutions actually back upstream into the community, which helps us and also helps the community itself. So specifically on the machine learning experimentation management side of things, we opted for MLflow. And for us, it automates model tracking and monitoring significantly. We automatically log parameters and metrics to our tracking server, and then our ML developers use MLflow's UI to inspect models' performance and compare the different model versions, as we talked about on the previous slide. We're not going to spend a ton of time talking about it, but on the serving side, MLeap is used for model serialization, so encapsulating a model into something we can reuse, and then also for deployment and inference serving. This is a super fun space to talk about. It's something I care about a lot, but it's outside the scope of this talk. So catch me afterwards if you're interested in going deep there. So I mentioned at the beginning of the presentation that it's actually quite easy for even the most advanced machine learning teams to become confused about what they're actually trying to accomplish when it comes to experimentation. So to recap, the goal here is to produce a machine learning system that functions reliably for a given set of tasks, those tasks it was designed for, and then can replicate that performance at scale. So to get there, we need to run a lot of experiments, but we also need to test. And those are not the same thing. So from the dictionary, a test is defined as a procedure intended to establish the quality, performance, reliability of something, especially before it's taken into widespread use. And you contrast that with an experiment, which is a scientific procedure undertaken to make a discovery, test, hypothesis, or demonstrate a known fact. And so the important thing to keep in mind here is that in an experiment, we actually don't know what the outcome is going to be. It's not deterministic. We're in the probabilistic space by definition. And so we're going to need a hypothesis in order to give some intuition about what we expect to happen and then observe a real world result. So at Yelp, we actually have a slightly different way of thinking about this hypothesis-driven experimentation, which is connected directly to its impact on users in the business. So on the one side, we have multivariate experimentation, and the key sort of decision factor here is this going to have an impact on users or the business itself? So will we ship this? We'll ship this in the terms if the model provides success as we defined it, and we won't ship it if it's a failure. And that's the most common use case we have. But I will mention that the test use case that we talked about in the previous slide also exists, which is that we don't expect there to be any impact on users, but we will ship them either way as long as we don't break anything. And so that's typically reserved for upgrading backend services. Okay, so now that we have that vocabulary, let's talk about how we might use this experimentation paradigm to help us find the best model performance in a post-production but limited production, post-deployment but limited production use case. So as a machine learning developer, I'm going to need some things to determine which one of the model experiment runs that I've done is superior in the production environment. And when I say that, yes, I mean anyone that's writing machine learning code. So it could be a data scientist, a machine learning engineer, an applied scientist, a research engineer, whatever one of the titles we give ourselves that particular week. And so the things that we need are a framework to identify the best performing model candidates, to be able to evaluate those model candidates to maximize or optimize against business driver or metric. We need to be able to track those performance KPIs that I talked about in the previous section. And finally, to be able to inspect and compare them. So breaking this down, at its most basic, we first want to ask, what experiment design do we actually want to implement, and what is the ultimate purpose? So if you can't fill in the boxes in the template that's at the bottom of this screen, then there's probably still some outstanding discussions or research to do before you can move forward. And at Yelp, we're actually quite strict about this. So to give a real-world live production machine learning product example, we're going to use this popular dishes use case. So popular dishes uses machine learning to highlight the most talked about and photographed dishes at a restaurant. So we do this by gathering some user opinion, images, and we try to present that to consumers on the platform in one place. And to do this reliably, there's a lot of complex fuzzy text matching, as well as some genuine inference of restaurant menus, since we don't always get restaurant menus from the businesses, believe it or not. So the feature ultimately had to scale to nearly every restaurant, food and nightlife business in the United States and serve millions of users in near real time. So we've got all those elements that we talked about before the top of the talk. And as you can see, before running a lot of experiments, we were able to very cleanly build a hypothesis and attach known metrics. So these are known to Yelp to evaluate success. And it's broken down right there at the bottom of the screen. And our key metric here is the impact on the number of meaningful connections that we have between these types of businesses and users that are looking for restaurants at that time. So as you might expect, there are a number of different personas that are involved in designing and implementing and evaluating an experiment of such a scale. But it's important to point out here that product managers are the owners at Yelp of the metrics themselves. Data scientists are responsible for researching and understanding the interaction of metrics, as well as providing those queries and metrics definitions from a technical standpoint to the engineering staff. And then determining what the minimum detectable effect, or like what we actually care about, or the threshold for which we care about, is the machine learning developer's responsibility. So just wanted to give some idea of how all those roles work together to get to an experiment that can actually run at scale. So you might be wondering at this point, okay, we feel pretty good about how to approach experiment design pre and post deployment, but so much of production outcomes are at scale. So, you know, what is the importance of these sorts of considerations for experimentation at scale? So as I mentioned at the top, we need things to be, one of the things we need to be able to do really well is test how the machine learning system scores data in near real time as unseen conditions and users are presented. And Yelp approaches this through our experiments platform called Bunsen. So today, nearly all data experimentation, and that's anything from products to AI to ML, products, AI, and ML, are done on Bunsen. And there are about 700 experiments in total being run at any given time. So it's quite a few. Bunsen supports the deployment of experiments to large but pretty segmented parts of Yelp's consumer population or customer population. And it also enables data scientists, machine learning practitioners to roll back any experiments if we need be. And we'll talk about when those conditions might come up. So from a really high level technical perspective, Bunsen consists of a few different parts. The front end is called Beaker. And so product managers, data scientists, analysts primarily use the front end to interact with the tool set. The main use case here, beyond setting up an experiment, is actually the scorecard, which we'll talk more about later, which facilitates the analysis of each experiment run. The meat and the sort of engine behind experiment analysis is done around the Bunsen experiment analysis tool packages, and those are called BEAT set of libraries. And then finally, there's a logging system that's used to track user behavior to serve as a source of features for AI and machine learning models downstream. And when I say features in this context, I'm referring to measurable properties of the phenomena that we're observing during this process. So the Bunsen client libraries have a couple of responsibilities. The first is to randomly allocate request cohorts in a deterministic manner. And so every experiment run that is started has that cohort allocation logic assigned to it. And an experiment can have multiple runs. It can either be an AA test or an AB test. And the sort of second capability of the client libraries behind assigning cohorts is to record events, so logging. So, for example, any event which can be requested requested to the system is loggable. So to do the allocation, there's actually a library that's written in Rust called the core allocation logic. And it's designed to work across all of Yelp's platforms. And when I say platforms here, I mean Insight, iOS, our web application, and Android. And each platform has a wrapper library for that. So once we get an experiment run, in this case, a model run, running on production, a scorecard is going to be produced for each experiment, as I mentioned. And the purpose of that gives product managers, business users, some information to be able to make some actionable decisions on whether a cohort within the experiment should be shipped. And if they decide to do so, we can promote the cohort to production by just changing the default value of the parameters being experimented on. And that's essentially pushing it to 100%. So a while back, we ran an in-product survey about dietary restrictions. And the goal here was just to try to understand from people who actually required dietary restrictions some specific questions about the types of accommodations that these people most utilize so that we could present them with the right information and make better recommendations. It's a lot of what we try to do at Yelp. But we don't just survey questions in a binary fashion. There's actually a graduated set of questions, some of which are more involved and harder to answer, that we present based on our overall understanding of a user's journey at the time. And that's machine learning determined. So in order to present such a thing in a way that doesn't violate all kinds of probabilistic laws and ensure that we can observe a significant result, we use Bunsen to assign and keep track of the user cohorts and apply these treatments, in this case, a set of questions assigned by a machine learning system over time. So that's a real world use case of using Bunsen for machine learning testing. It's a bit hard to see, so apologies for that. But what you're looking at is an example of the scorecard that I just mentioned before. That's generated once an experiment run is complete. And for each cohort per metric, you get the absolute lift, the relative lift, our winning probability, and an indication of if the experiment has violated any of our corporate level metric thresholds, which we call guardrails. So we've considered so far a relatively information-rich environment. That is, we've assumed that we have a pretty good idea about who the end user is and what a good outcome would be. But what if we didn't? So it turns out this is a super common problem, especially in marketing and advertising. And in machine learning terms, we may have some priors that we want to take advantage of, but in a fully powered experiment model, it might be hard to incorporate such data without peeking into an experiment run before it's complete. And that's bad. Like, that's actually something that there's lots of literature about not doing. So how do we do this without breaking things? So one option might be to use a technique called sequential testing, which would involve making a decision during an experiment by sequentially monitoring data as it accrues. But the problem with that is that we'd still need to run a bunch of experiments over time to get to the best outcome. It just would take us less time to get to power. So that doesn't really solve our problem. But another approach, which is particularly relevant for the machine learning use case, is multi-arm bandits. And so we're going to spend a few slides talking about that before we close up. So if you're not familiar, multi-arm bandits is just a set of algorithmic techniques that are used to dynamically allocate traffic to different variants, the ones that are performing the best, while actually demoting or sending less traffic to variations that are performing as well, according to some objective measure that is set during the setup of the technique. So you get a better result essentially from the experiment faster because there's no single best outcome. You're not optimizing for a single experiment run outcome. And there's a number of algorithms that I don't really have time to go deep into today that can be used here. And we've taken a look at Yelp at kind of all of them and are available to some degree in different parts of our infrastructure. But the one thing that's common about all of these is that they have sort of a general assumption that you don't really have a lot of information. You don't have priors about how a user or how a business or even the model itself, in our case, has performed. And that's just not really the use case we're in. We actually aren't in an information poor environment. We do have some prior knowledge about Yelp user behavior and the model's performance against that behavior. And even better, we have some information about how people are using Yelp. So we can make some inferences on their intentions as well. So if there was a way for us to give context to the bandits that we talked about in our previous slide, wouldn't they be even more efficient and more capable in their routing activities? Well, the answer is yes. We do have that information. Yes, there is a technique. So it turns out what we are trying to apply using that idea in 2021 is a technique called contextual bandits. So instead of focusing on serving slightly different design layouts or ad copy, which is really common for bandit use cases in the previous set of techniques, we're pulling it back a step to using a technique to decide which actual inference engine is best based on our contextual knowledge of a cohort of users. So what we get out of that is the best performing model at the time for a given user behavior category. And the best part about all of this is that it can and will change. The model or the inference engine we're using can and will change over time as we gather more information. So there's a lot of math involved in that, and I don't have enough time to go into it, and I want to make time for some questions. So I think we'll leave it there. But hopefully after this talk, you have a bit better picture of some of the considerations that are important to keep in mind for designing and implementing machine learning experiments for large-scale machine learning systems. So I'll go ahead and pause there and open it up for questions.
All right, thanks so much, Justin. That's awesome. And actually a great compliment to the conversation we were having in the keynote on some of what LinkedIn was doing with experiments. I'll give folks a time to get their questions into the chat. While we're waiting, though, you didn't spend a lot of time on the platform elements. You kind of flashed that up and said that you didn't have time to talk about that. Do you have maybe a minute on how all of this is incorporated into the platform?
Sure. I mean, I can even go back and kind of talk a bit more about it. So there's a couple of different ways to talk about it. Maybe I think I should speak here. There's a couple of different ways to talk about it. So this allocation engine or these experiment logics actually tied directly into our logging system. So it can query directly the machine learning results that we get from our experiment runs. It can query directly the product data that we're receiving from user interactivity. And it can use that as a mechanism for making a decision about which users are placed into which cohort. So from a platform perspective, really what we've done is we've stuck in a dynamic user allocation or cohort allocation logic on top of our existing platform infrastructure. So, if people are curious, we spend most of our data warehousing in the Redshift family of tools. And then from machine learning perspective, most of the model development and inference is done. You've seen MLflow, so you might imagine Spark is a big component of how we're doing our development cycle. And then from an interface perspective for developers, it's primarily Python as an experiment and test language. And so we're essentially calling, containerized environments that run Spark code at a relatively low level, and then are providing an inference that is then served via this cohort tool to users. So from, if you're tracing the lineage, if you're a user, you're essentially interacting with something that has talked to all three of those different capabilities. And then you're on top of the whatever platform you're doing, iOS, Android, or web, you're interfacing with the platform at that level.
Got it. And this seems like the kind of tool that folks might want to see open source at some point. Is that possible? I'm not going to let you comment on the future or ask you to comment on the future, but is that I guess what I'm curious about is it so specific to the way Yelp does things that it couldn't be open sourced, or is it something that could be open sourced?
No, I don't think there's anything prohibitive. We just haven't gotten around to it. I think like if you want looking for a real world contemporary on this part of experimentation, so we talked about the two different parts. One is, you need experiment management for development cycles. So like there's a lot of people going after that problem
there.
But for the sort of large scale ML dependent or ML specific, customer or product facing experimentation, there's fewer. But Optimizely has been going after this for quite a while. And so if you're looking for a real world sort of example of what this looks like, their tool is one that is very similar. And if we get to a point where the community does want that, we certainly will take a look at it. And we just haven't gotten around to it yet, but it's certainly possible.
Awesome. Well, Justin, thanks so much for joining us and for a great presentation.
Thank you. Bye-bye.
Thanks.